Montshire Museum of Science. My name is Marcos Staffney. I'm the executive director for the museum, and I'd like to welcome you all to our Montshire Tops Space program this evening, from video games to satellites, with Dr. Carl Brandon, who's right there, and is going to give an amazing presentation about CubeSats and all sorts of other things this evening. As you know, or as if you don't know, the Montshire has an amazing exhibition called Destination Space right now, which puts together 3 excellent exhibits. One art exhibit by the artist Ned Kahn, who looks at how we might perceive or think about surfaces and atmospheres of other planets. We have a commemoration exhibit about the 50th anniversary of the moon landing that is out there, and we'll be having a big celebration, an event for that anniversary in July. And then a wonderful exhibition co-produced by both NASA, the Science Museum of Minnesota, and the National Informal STEM Educators Network, called Sun, Earth, Universe, which really looks at how we look out into space and the type of technology that we do to find things out in space. So without further ado, I'd like to introduce Dr. Carl Brandon. From working on a cyclotron and earlier video games to flying airplanes and launching satellites, Dr. Carl Brandon's diverse background has led him from IBM to Vermont Technical College. With a PhD from the University of Massachusetts at Amherst, Dr. Brandon has been teaching at Vermont Tech since 1977. Having worked on 30 NASA-funded projects, Dr. Brandon and team constructed a CubeSat that was launched in an Air Force Minotaur 1 rocket in November 2013. It was in orbit and operational for 2 years, and it is the only successful satellite of any kind launched by a college on the East Coast in the United States. Ladies and gentlemen, Dr. Carl Brandon.
Can we turn these lights off? Because they're on the screen yet. Okay.
And he drives a Tesla.
Okay.
What? Yes.
And he drives a Tesla.
Yeah. And a former student is here who drives a Tesla too. They're parked side by side. So what I'm going to be talking about tonight is how I got involved in the space stuff. So I need to get the lights turned down so we can see the screen. Somebody doing the lights? Yeah, there we go. Okay. So you'll see it again just by itself, but the background here is the first picture we got back from our satellite. It's the north coast of Western Australia, along here. And that's, I photoshopped in what our satellite looks like, since it couldn't take a picture of itself. My background is, when I was about 6 years old, there was a series in Collier's magazine, a no longer existent magazine, as many are not, in the 50s about space. And they had Wernher von Braun and Willy Ley, a whole bunch of the rocket scientists involved with this. And the pictures in there were great. They were done by people like Chesley Bonestell. If you've been to the Air and Space Museum in Washington, when you go into, you'll actually see a picture of the mural later on with me standing in front of it, of his. And they were really quite neat. And the thing that's really interesting is how close they were to what actually happened later on when we had the space program. So this is their vision of a lunar lander, and it's not that different from what we actually had. This was their idea for a launch vehicle. The upper part with the wings that was not the first one went to the moon, but later on when they did the space shuttle, similar to that. They're using hydrazine and red fuming nitric acid for the propellants, and those were a little different. We use in a number of spacecraft today hydrazine and nitrogen tetroxide, which is the fuming part of the red fuming nitric acid. And my first rocket was a gunpowder-powered rocket. We're actually using our satellite software. There's a group at the University of Bridgeport, and one of the people that came up and visited also went to the same elementary school about 5 years after I was there. And my uncle was an 8th grade science teacher. He gave me a chemistry set when they had real chemistry sets. And I went to the library and looked up how to use the ingredients that were in the chemistry set to make gunpowder, made a rocket, brought it to show and tell in first grade, and asked the teacher if I could fly it across the playground that you're looking across here. And I started over there, and it flew across the playground, and the teacher had to clean out her pants afterwards because she had no idea it was a real rocket. So I didn't remember her name, but I remember Mrs. Baker, the principal. We spent a lot of time together during those years. And for 8th grade science fair project, I have up here a bunch of instruments There's a Geiger counter which I built, and a UV sensor, the humidity, temperature, and some other things, and then a mechanical multiplexer, a little motor that had a brush that went around to the various contacts, and then a little one-tube radio I built. I use a regular radio receiver, but then there's an oscilloscope which I built from scratch, which was displaying the data. That was my 8th grade science fair project. So I got started in this thing early, and then I went to Michigan State. And I got involved by one of these things that's complete chance, which when you're advising people where to go to college, probably 90% about how great an experience you can have is complete luck. I got an advisor who was in charge of the cyclotron project. He was the top cyclotron designer in the world. And as a result, the summer of my freshman year, I got to design part of a cyclotron, which if I had been at MIT or Harvard, only grad students would have done that. I would never have had that opportunity. This was the first computer we used. It's a vacuum tube computer called Mystic. It was a copy of ILLIAC one at the University of Illinois. It had 40-bit words, and there were 1K of words. So it's 5 kilobytes of memory in this thing. We used electrostatic storage tubes. And there was one tube, cathode ray tube on the front that could display one of the bit planes. So it was a 32 by 32. It was a 1 kilopixel image, and you could have the switch to go any one of the 40 planes. But you could program things to illuminate pixels. And so I wrote a video game, which was a space war game, not very high resolution, but as far as I'm able to tell, it was the second video game ever written in the world. MIT beat me by about 3 months. The more interesting thing is that within the next few years, as other universities got computers, lots of people wrote video games, and they're all virtually identical because all computer nerds think alike. And none of these people had contact with each other, so they independently developed the same game over and over again in many different places. Some facts about it: 2,610 vacuum tubes, and you saw a picture of it, the size of it, the electrostatic memory. We had a teletype printer on the output, 10 characters per second. And then a 12,500 word magnetic drum storage. And input was a Freedom Flexowriter, which was a typewriter with a paper tape punch and reader, the first word processor. So you could do a form letter on punch tape, and then it would stop, allow you to type in the salutation, and then continue doing the letter. And we used it to punch out the paper tape and then for programs, and then feed it back into the computers how the program was loaded. We then got a control data 160A, which is shown here, and that's a desk-sized small computer that was used, well, we initially had it just by itself for a few months, and then it was used for input into the control data 3600, which when we got it was the largest computer in the world. We had the first one. And I then got myself a job as a computer operator running from 11 at night till 3 in the morning. So I had the world's largest computer as my personal computer, and I used to get multiple runs per night where nobody else could do that. And of course, that's not nearly as powerful as my wristwatch today. That's my advisor with a 1/4 scale model of the magnet for the cyclotron. And that's a probe that's going in here run by a milling machine, a Hall effect probe, to measure the magnetic field. This was a sector-focused cyclotron, which has a spiral-cut pole faces for the magnet, so that the average magnetic field can increase in intensity as you go out as the particles gain speed, because they gain mass because of relativity. But if you just did that with a straight, flat pole face, you would be unstable and the particles wouldn't stay in the machine. So they have spirals, so the things wobble up and down, but they can't get too far out of line as they go around. They were proposed very early after the first cyclotron was designed, but they didn't have the computers to be able to design it. So this was one of the first that was ever done. And here's the full-size magnet when it's being tested. You can't really see the spirals, but there's somebody looking inside the magnet. You get an idea of the size. The windings for the magnet here are 1-inch square copper tubing with water running down through it for cooling. We ran 10,000 amps through that. I designed the extractor coil, which was to cancel out the main magnetic field to allow the beam to come out of the machine. And it was made out of 1/4-inch square copper tubing. There was 4 different rectangular pieces that also had 10,000 amps. And no one thought about what the forces would be on it. So the first time we turned it on, the rectangles became circles and threw fiberglass all over the room. So we had to have it remade with a big aluminum frame to hold it together. This is the relatively complete machine, give you an idea of its size. The concrete walls behind it and on the side are 10 feet thick, iron-filled concrete. This is a door. You're looking at the top of the door. It goes down into the floor. It's on a hydraulic lift, and then it goes up here and seals to close it. Those doors were 56 tons, and above here is a traveling crane, which is a 40-ton crane that would be used to lift it. So it was a little overstressed, and at one point they were lifting a door into this frame, and they hit the edge of the frame, and it pushed the cable to the side, and it broke the cable, and the 56-ton door dropped about 8 feet, and it dented the concrete. I didn't know concrete could be dented, but that did. I got a summer job after my bachelor's working at IBM's basic, well actually no, this is still I'm looking ahead, there's a double picture here. Extractor coil is in there, and there's my advisor with the finished cyclotron. So the summer I got a job at Yorktown Heights IBM Basic Research Center with, it's full of Nobel Prize winning scientists, and it's a really nice building. It's an Saarinen building out in Yorktown Heights up in, as you can see, a very rural area, about 60 miles north of New York City, or about 50 miles north. And I worked on studying magnetic properties of europium oxide. So I wound up making a completely automated experiment. It took me about a month to get that set up. And then I'd come in the morning and I'd turn the thing on and I'd go out and sit under one of those trees and read a book till time for lunch. I'd go in and have lunch, I'd go back out, read the book some more, go in at about 4 o'clock, turn a switch, and it would punch out on cards all the data that had been collected during the day, and I'd take it down to the computing center. Next morning I'd pick up the results from the computing center and repeat that process. It was a really nice summer job. And this is the kind of computer memory that was used at that time. It's a magnetic core memory. This is also used on the Apollo missions. And there are little donut-shaped cores with 3 wires running through them, horizontal, vertical, and then a diagonal one. And they're relatively big. They work fairly well. They're not real fast. And so IBM decided to make a memory chip. And so this was, I believe, the first memory chip in the world. And we designed it on a surplus SAGE terminal. These were the NORAD aircraft defense radar terminals with a light pen, which is down in the lower right. This is a light pen down here. Instead of a mouse, you would point at things, and the computer would know where you were pointing. And so we designed a whole thing on that. And as far as I know, this is the first complete computer-aided design and manufactured project of any kind in the world. So my group was writing the software to do this, and I was doing design on the chip itself. There were 3 of us who worked on the chip. And that's a picture of the chip laid against the cores in the background. So you can see the individual bits of core here, and then this thing is it's only 128 bits, but still it's a lot more compact than the core memory. And they made several $1 billion worth of those things. Here's the layout on the chip, the various parts, the main memory here, and then there are driver circuits and read circuits. The metallization pattern looked something like this. I mean, it looked exactly like that, in fact. And so we designed the chip over a period of about a year, and it was very successful. It was used in the IBM 370 series of computers. Unlike many of my friends who got into flying, I didn't do that as a kid. I mean, I actually could bicycle to an airport. I did, in fact, bicycle because I had a friend who lived across the street from it. That was about 2 miles from my house. Mostly I went there because I could stop on the way. They had homemade donuts at a place that was about a half mile from the airport. They were quite good. But then I started flying at Michigan State. They had a flying club. I got my private pilot's license. And during my freshman year, I found a copy of Soaring magazine on a newsstand there. And the picture of the glider was just so beautiful that I bought the magazine. I've never again seen a copy of Soaring magazine on a newsstand. They had a $3 a year student membership, so I joined it. And I never saw a glider, in person until 3 years later, when leaving Budapest, heading west, there were gliders on the ridge, but we couldn't stop. I had 7 of us traveled around Europe and the Soviet Union that summer. And but then a few days later, we were coming into Salzburg, and I saw a glider, and I followed it until it landed, and told my friends to leave me there, and I negotiated with sign language, because at that time I didn't know any German. And I got a 1-hour flight. We went up over Hitler's hangout, Berchtesgaden, and it was a beautiful area to fly a glider. And when I came up to Vermont, I joined a glider club over at Sugarbush Airport, and that's the glider. I was a club member. There were 10 of us who owned that glider. And I'm in another glider taking a picture of the one that I was a part owner of. And then I bought a plane, Cessna 182, and I did 3 trips to the West Coast in that. And I actually have an airstrip in my backyard that I had landed on. And I did a little personal aerodynamics research when I was at IBM, did a lot of skydiving, about 120 jumps. My roommate took that picture. And then here's one of the gliders that we have in the club over at Sugarbush now, and that's my son at age 10 in the front. I started giving him flying lessons when he was 8 years old. One of the things about I was 60 when he was born, so as an older parent, you're involved in a lot more things, so you can do a lot of fun things that you aren't able to do when you're a younger parent. And I was doing sailing up in Malice Bay. That's the Intrepid, the only 2-time winner of the America's Cup, and I was able to crew on that for a couple of summers. And that boat was really neat. And for my master's degree, I made use of my flying and all of that, and I studied seagull soaring flight aerodynamics. I had something that almost anyone on the coast would love to have. I had a federal permit to shoot seagulls. And if you've never dealt with seagulls, they're one of the nastiest birds in existence. And I had to collect a few of them to make measurements. And for my doctoral work, I studied bat flight. This is not one that I used for my doctoral work, but it's one of the fishing bats, and it's the first color picture ever taken of a fishing bat that I took at a friend's lab out in Albuquerque. And I used a slightly shorter wingspan. This is about a 2-foot wingspan. The ones I used were 18-inch wingspan that also skimmed the water, but they picked up insects rather than fish. I did a little physics experiment on an inelastic collision with my Saab. I ran into a moose at 80 miles an hour. Testing Saab's design. It's the only car in the world that was designed for and tested for moose collisions, and in fact it works exactly the way the test showed. All of the internal organs of the moose wound up inside the car, the rest of it went over the top. Both doors still worked perfectly well. We just got out and walked away. And grossed out the ambulance people and the ER people, but I had a few little tiny cuts. I didn't even have a Band-Aid on afterwards from the glass from the windshield. I also did some experiments in gravitational potential energy. I got a blasting license, and the guy who taught me bat photography, where I took that picture, he was a blaster, and he taught me how to do explosives. And so this was the front page of the local paper showing a silo, one of my colleagues, as I brought it down with explosives and standing on the rubble at the bottom. Again, as I mentioned, you can do some things having a child later. Here's my son at 8 years old starting up a nuclear reactor at RPI. And he did that 3 times and then scrammed the reactor with the red button there. We didn't have a meltdown, so he did pretty well. And when I got involved with CubeSats, sort of with the information from a friend of mine who was my next door neighbor growing up, I was just at his 75th birthday on Sunday, down near Nashua, and he told me about CubeSats, and so I was getting involved reading about them, and I actually got a kit to build a CubeSat. Actually, that's the one that's sitting on the table there. It's the one I got initially. And I was looking around on the web, and I came across this drawing. So this is at Aalborg University in Denmark, and it's a drawing of a single CubeSat like the one on the table there, with little legs and a little rocket engine, a little rover coming off, as a lunar lander. This obviously somebody had a lot of free time on a rainy day and spent some time with their CAD program doing this. And I looked at that and I said, well, the propellant tanks, they're about the size of ping pong balls, are too small, that would never work. But it got me thinking about whether you could make one that would work. So I sat down and did a preliminary design, and it looked like you could. And then I did a very detailed design, and there are 3D printed models of them on the back table there. This is the model, the smaller one that you're seeing back there, and it's got 4 propellant tanks. The one back there was our initial design, which had hydrazine and nitrogen tetroxide. And one of the people at NASA said, well, the only problems with hydrazine is that it's toxic and it's carcinogenic and it's flammable and explosive, so they probably won't let you use it at the university. So there's a monopropellant that was developed actually to shoot artillery shells at NASA Glenn, but That is available, and I'll show you later, an engine you can buy off the shelf that uses it that's of the size in this CubeSat. So I was the first person to talk about sending CubeSats to the moon. I mean, that drawing existed, but nobody was serious about it until I started looking at it. And so this is the Chesley Bonestell drawing up here in the background, and I'm all dressed up in white tie and tails, which I have that outfit because you get to use it so much in Vermont. And I actually have worn it a lot at the wall seating before Vermont Symphony Orchestra. Kansas stopped doing that. It was really sort of neat because I was invited by the Moon Society, and the other invited speakers were Scott Carpenter, John Glenn, and Buzz Aldrin. And Carpenter and Glenn were there for this reception where the picture was taken, but Aldrin was there for the whole concert. And I had a conference, and I had several discussions with him. And he was very interested in our CubeSats because unlike all the other astronauts, he was not a test pilot. He was a fighter pilot from the Korean War, F-86s, and he wanted to be an astronaut. And he figured he had to do something special to be able to do that. So he went back to MIT and got a doctorate in orbital mechanics. And he, in fact, designed the flight paths that took them to the moon. And he has designed a path called an Aldrin cycler, which allows you to orbit the Earth and the moon without any rocket fuel being expended. And then you would have it as a ferry. You'd ferry cargo up to this thing. It would then go to the moon, and you'd ferry it down, and it would save a lot of money. And to test something like that on a larger scale would be probably several $100 million. But with self-propelled CubeSats, which we were working on, you could do it for on the order of $10 or $20 million. So he was very interested in that. He's the only one of those astronauts who's really active in the space field. This is the thruster that's available. You can see its size compared to a penny from Busick, a company in Natick, Massachusetts. It's a half a Newton. Which is roughly the weight of 50 grams or a couple of ounces in thrust, and that's all you would need on that thing. So at another CubeSat conference, somebody triggered my idea with something. I don't remember what it was, but I wondered whether you could take that single CubeSat there. That was designed to land on the moon. But my initial idea was, okay, somebody takes it up, an astronaut, and they toss it out the window, and it could land itself on the moon if you were orbiting the moon. But then I started thinking about getting it to the moon. I mean, finding an astronaut to carry it's not easy. So I designed the bigger one that you see in the back table, which is the booster. If you got a ride on a communication satellite launch, which puts you in what's called a geostationary transfer ellipse, this thing would give enough thrust to leave that, go to the moon, and get in orbit around the moon, carrying that other one, the small one. The small one could then go and land. It's not terribly practical because there's so little space available for any kind of instrumentation that you couldn't do much with it, but it's possible you could do that and land on the moon. The other option would be to put an ion drive in there, and we're initially looking at making our own ion drive. And this is the 3U CubeSat, which would be the two of those things in the back stacked together. And these are photovoltaic panels that are folded out. That's not a great arrangement for photovoltaics. You can buy off-the-shelf ones now that are much better. You'll see pictures later on. This is the completed CubeSat that we used before launch. This is the one that orbited the Earth for 2 years. The photovoltaics are on the side. These are, now the ones you have, if you have photovoltaics on your house, cost about $2.50 per watt. These are $300 per watt because they're 30% efficient. And that little extra bit of efficiency costs a fortune, but you don't have much space on a CubeSat or in any spacecraft, so you have to pay for that. There's the camera. It's covered with Kapton tape for a vibration test, and then that's a GPS antenna on the top. There's some specs about our thing. 11,071 orbits, 293 million miles, equivalent to 3/4 of the distance to Jupiter. We launched on an Air Force RS-3 launch, a Minotaur-1 rocket, where the first two stages are the first two stages of a Minuteman ballistic missile, and the upper two stages are the second and third stages from a Pegasus airdropped launch vehicle you'll see later on. We had to do a vibration test. This is down at BA Systems in Nashua. You can see that's a little box aluminum thing which holds the CubeSat and bolts it down to that table. If you would stand on that table, that can go up and down about 3 inches fast enough for 100 Gs of acceleration would break all the bones in your leg. But because of a lot of high frequency vibration in this rocket, we required the largest vibration table that's available in order to do this test. We also had to do a vacuum thermal bakeout to make sure you didn't have any volatile materials in there that would condense on other people's instruments. And this is down at UNH. UNH had built a lot of instruments for spacecraft, but not their own spacecraft, until 2 weeks after ours. They launched a CubeSat, but it didn't work, which is the most common fate of CubeSats. And here are some of the parts of the CubeSats. And so there's a GPS board, only $3,000 for the GPS. Actually, the GPS board, which is this part, was $3,000. And there's a board that it mounts on. I forgot what that was. That was around $1,000, I think. That was made at University of Michigan. Here's a fold-out antennas are coiled up under this thing with little doors that open up, cross dipole antennas. That's a $7,000 antenna from the company is called ISIS. It's not the one in Syria, it's the one in Holland, but they unfortunately chose the same name. This is the board we have made LED dynamics designed at. It has 2 hysteresis rods, and what those do is we stabilize this thing, and I'll show when we see the thing put together, you'll see it. There are 4 magnets in the corners of the satellite, so it lines up with the Earth's magnetic field. But when it gets ejected from the spacecraft, if it's wobbling, there's no friction, there's no air to stop the wobble. It would go on to do that for months. So the hysteresis rods absorb that energy from the magnetic field. It works against the Earth's magnetic field and will stop the vibration in about a day or so. And then that's the GPS antenna. Here's a bunch of sockets here that the photovoltaic cells and we have LEDs on them. You'll see later on. They all plug into that board. Here's the board with some other stuff put on it. The camera, that's a $20 camera that took all the pictures. The GPS antenna, it has extra high gain compared to a regular one. There's an inertial measurement unit there that was donated by a company up in Williston, and the hysteresis rods you can see there. Here you have some other things showing a $20 camera and the $1,500 value for the IMU, and some of the other parts that I just pointed out. And here I was assembling this thing. So at this point, when I'm assembling this, the software, which is our unique thing, was a technology that I chose. We used the Ada language. Ada is named for Lord Byron's only legitimate daughter, who, I mean, I was trying to figure out where she got her brains from. It wasn't from Byron, but her mother was a mathematician. And she was about 150 years ahead of her time in thinking about computers. She described how to program Charles Babbage's mechanical analytical engine in the first half of the 19th century and described what could be done with computers, basically what kinds of things we're doing today. That was a fully capable computer, all mechanical, very slow, and not much memory, and it was never fully built by Babbage, but it was built about 50 years ago and worked completely, and she was the one who described how to do it. So the language is named for her. It's one of the few languages that's not an acronym. My colleague Peter Chapin, who was supervising the students working on the software, he was doing his PhD dissertation at this time, so he was not available. So one student who did about 80% of the software was sitting in the room with me with his laptop while I was doing this, and we literally couldn't talk to each other about the software because we were too busy. And it was pretty good. It worked where most people's do not work. There is the thing finally put together and assembled, and here we are testing the LEDs. It was designed so that with the LEDs, the question was, could you see them with the naked eye? And with the calculations I did, you would get about 300 photons in your eye, and that's enough that the sensors in your eye could see that, but your brain suppresses it until you get about 500 photons. Unless you take LSD, that turns off the suppression, then you can see it. Here is the getting ready for the launch. That's the rocket in the background there. My son and the student who did most of the software and his girlfriend who did a little work on it, getting ready for the launch. And there's the rocket during the daytime on the launch pad. The yellow part is a Minuteman II ballistic missile with covers for environmental control to keep it at the right temperature and humidity. Probably didn't need that, but it was designed to have those controls when it was in the launch silos, so they decided to do it just to be safe. The upper stage that's in white is from the Pegasus, and here's a picture of a Pegasus being dropped from an aircraft, and that's a small launch vehicle that does that. Here is the picture of the launch. It was a night launch, which was pretty neat, about 18:15 at night. And let's see. Okay, why are we not seeing this? Shoot. I've got something on. Let me see if I go to full screen. We're not seeing. Why does this not? Shoot. Just a second. No, I gotta get the other image on here. Just a second. Shoot. It's showing up on my computer, but it's not showing up on the screen. Let me reduce this. Reduce this, and I'll just try up here. See if this works. Nope, that's not working. Shoot. Okay, let me stop that again. What's going on here? Maybe if I just stop this thing. The slide, oh, actually, that's probably what I have to do. Just get out of the slide. Oops, that's not it. No, I'm not seeing that one. Oh, here we are. I'm in the slideshow. This is, what are we, I'm just gonna have to, I think I'm gonna have to stop this one. Come on. Okay, maybe this will work. Let's try this. Yep, there it goes. So this is a video of the launch. NASA bought me this nice $8,000 video camera setup. And all the sound in the background are people who have CubeSats on this vehicle, so you'll see they're rather enthusiastic. Pieces of solid fuel coming out the back. I was able to film all 4 stages igniting, which was pretty neat. And there's the sound finally reached us. We're about 3 miles away. So most of these people have worked 2 or 3 years on a CubeSat, so they're pretty happy to see it finally launch. Originally, they told us it was going to cost $30,000 for the launch. Launches were costing $125,000 or something, and NASA finally decided to sponsor them in their launches. But they were going to initially charge $30,000, and then eventually, you'll see the staging occur here in just a second. There it goes, separated the first stage from the second stage. You'll see the first stage tumbling off to the right, it's glowing red. And the second stage has partially ignited, and it will fully ignite in a couple of seconds. You'll see that, and then I'll end the video. So they said it was going to be $30,000, and then it turns out that as long as you got your satellite on time, they weren't going to charge you. So as we say, you can't say there's no such thing as a free launch. So there it is, second stage.
How many CubeSats are on that one?
There are 28, 14 are Air Force CubeSats, 2 NASA, and one of the NASA's certainly didn't work. I don't know about the other one. We're the only one that fully worked of the 12 university ones. One worked for 4 months. 8 were never heard from. 2 had partial contact for 1 day or less. And ours worked for 2 years and 2 days till it burned up. So that was, I gotta go back to this thing. I don't know why this thing does not just display what's on my screen. It's sort of weird. Oh, that's not going to make any difference. Okay. I'm just going to have to go. Okay, here's our first picture. North coast of Western Australia, and the missing Malaysian airliners up there. It was just, I was stunned when we got this picture back. It was our first picture. That's a $20 camera. And it was a good deal. Here's some other pictures it took, and then there's a poster on the side. After we can turn the lights up, you can look at them and a little closer. We discovered there are a lot of clouds on the Earth. That's what most of the pictures show. But most of them we didn't keep track of where it was, but a few we did. This one's Africa. We found a few others where we knew where we were looking. More clouds. This was my idea for a large area orbital debris mitigation. One of the problems is space junk. This thing has 5 kilograms of californium-251 with RDX explosive around. It's a small nuclear weapon designed to clear all the CubeSats out in the nearest mile or so. The problem is the californium is about $50 billion, and the grants are not easy to get for that amount. And there's some issues with nuclear weapons in space and treaties and stuff like that. But anyway, it was an interesting idea. It was a fun design. But I had a friend who actually designed nuclear weapons, and they actually talked about a nuclear hand grenade, which was based on this kind of thing. Had to have a good throwing arm. There were some posters from the ADA organization, SIG-ADA. I was their education chair at one point. I was involved with the ADA language when it first started in around 1980. The full version or spec was released in 1983, and I taught the first undergraduate ADA course in the world at Vermont Tech. And then here's one of the posters about our CubeSat. And so we're using what's called SPARC ADA. I don't know what the SPARC acronym is. People seem to have forgotten what it means. It was developed at one of the universities in England. ADA was developed actually in France. SPARC does mathematical proofs that your software is error-free. It's a totally different way to do software as opposed to testing. And I'll show some specs comparing it with other languages that people use in CubeSats. So we were in the first group chosen for these free launches. We weren't in the first launch because you got assigned to a group, and then it depended on which rocket you got assigned to when that rocket launched. Some specs on our software, about 6,000 lines of code, 4,000 lines of comments, and so on. So SPARC is annotations. So those are comments that the SPARC tools use to understand more about what you're trying to accomplish with your software, and then it does mathematical proofs. It generated 4,542 verification conditions. Those are things that it had to prove to show you had no errors in the software. Anyway, it worked amazingly well. SPARC ADA is used for every airliner software, every air traffic control software in the world. SPARC is a newer technology. It's used in the new UK air traffic control system, the engine controllers for the Airbus aircraft, for the Trent Rolls-Royce engines, and a bunch of high-speed rail applications in Europe. And this enabled us to create software we had the smallest group ever to build a satellite, and I think that actually helped. But without these tools, we could not have finished the software in time, no question about it. So here's some failures that show that would not have happened if they'd used our technology. The Mars Science Laboratory, that's a $2.5 billion spacecraft that's running around currently on the surface of Mars. That had a memory anomaly. We'll show it to you later on. And then the Ariane 5, which is not the most recent, but the previous European Space Agency launch vehicle, had a failure on its first launch. And then the Boeing 787 has had 2 different problems. All of these would have prevented if they used SPARC. There was a study done by the UK Ministry of Defense on the C-130J. C-130 is a 4-engine turboprop military transport that's used by the US and all kinds of countries around the world. And what they found, that the error rate for C, which is the language used by everybody else's CubeSat, was 97 per 1,000 lines of code. This is the old ADA. ADA 95 was 25. For SPARC, again, the old SPARC was 4. And then NSA did a project, and they used the newer version of SPARC. And it's not the newest. It's 2005, which is what we used on that CubeSat. That was 0.4. So, there's like 240 times fewer errors compared to what most people are using, which is why their satellite didn't work and ours did. The other issue is that SPARC, because it's so efficient at finding errors, it takes less than a third the time to write the software to get it all finished, including testing and verification. So there's no reason not to use it. So people say, well, our students come and they don't know how to program in Spark. They know C because they learned it in high school. So here's some data I put together to show them why that's not a reasonable argument. Because of the productivity difference, so if two C programmers got started on a project and you take one of them and started teaching them Spark at the beginning on a program the size of the one in our CubeSat, at the end of 3 weeks, the new programmer using Spark 8 would have caught the C programmer and would have finished their program in just over a year. The C programmer would take over 3 years. The Spark program would have 4 errors, the C program 970 errors. And I can't understand why people don't use this. I talk to the people and try to convince them, don't understand it. So the Mars Science Laboratory, they had a problem where two pieces of software were trying to access the same memory location. That's not possible. You couldn't do it intentionally with Spark. But it can happen easily with C, and it did. They've, with the error rate that we saw, you would expect 35,000 errors on this piece of software, on this $2.5 billion spacecraft. NASA puts in an enormous amount of effort and money to reduce that error rate, but they still, last time I saw, they had corrected 1,500 errors. There's so many errors that they have a complete duplicate of the $2.5 billion spacecraft at Pasadena at JPL, which I've seen, that they have to test all the software fixes on before they send them up to Mars. The Ariane 5 on the initial launch on the left looked pretty good, but 37 seconds later didn't look quite so good. And they had an error which would have been prevented by Spark. I mean, you know, you look at the details of this. It was $500 to $700 million loss of that spacecraft, of the rocket and all the satellites that were on it. The Boeing 787, this had a thing which would keep track of power on time, which I've never been able to find out why one would want that. Just the time the aircraft's plugged in on the ground or it's running, either one. But it was storing it in a 32-bit register, which after 8 months overflows. And they didn't have any way to do that, to deal with that, except to put the computer in what the computer called a safe mode. But if you were in the airplane, that wouldn't be a safe mode because the airplane then crashes. And there's no way to recover from that. Fortunately, the FAA was testing this software in their lab. Boeing didn't catch this error, the FAA did. So they now tell everybody to make sure you turn off your software before 8 months. Then, about a year later, they found another one where you have to worry about turning it off every 3 weeks, or it can do a reset of the computers. That only kills you if you're taking off or landing, so it's not quite as bad. This is what we're looking at for our software for a deep space application. No one else is putting in the specific functionality for deep space. We're the only ones that have it in software so far, and this is what one of these things would look at. This is what's called a 6U CubeSat. It's like 6 of those piled up, so it's 4 by 8 by 12 inches, about 30 pounds, and those are 2 big photovoltaic panels. It's got an ion drive. You can buy those ion drives off the shelf for $850,000, which sounds like a lot, but you know, a $15 million spacecraft, it's not too bad, and allows you to do things that you couldn't do otherwise. And one of the deep space functionality we had, this, you'll see it a little bit, the ion drive can move just in 2 directions, back and forth and up and down, and you have 3 axes on the spacecraft, and to control the rotation on all 3, there was an algorithm developed at the Jet Propulsion Lab on how to do that with the 2-axis thruster. I happened to have lunch with one of the guys. After lunch, somebody told me, oh, this guy figured out how to do this. And I just sort of stuck it back in my memory bank, and then we were involved with the project a few years later, and I was able to dig up the information and got the detailed description of the algorithm, and our first master's in software engineering student at Vermont Tech did that for his thesis. And last summer I went out there, we demonstrated this to the guy who developed the algorithm, because they did this in 2011 and nobody was using it. And they had spent a couple of years doing this, and all of a sudden we come out and here's the software and here's an emulator showing how it works, and they were so excited to see that. I was trying to get a ride in this satellite, but I didn't quite fit. Here's a picture of the ion drive in operation. It's about an inch, that opening where the ions are coming out over here, about an inch across. And here's a picture of the whole unit that you can buy, with the ion drive is here that you saw in that other picture. This is what's called a neutralizer, little thing here. There's a motor for the gimbals that allows it to tilt left and right and up and down. Okay, and again, now I'm going to run into the same thing again. So I want to show you how this thing operates. So I've got to kill it, and yeah. So this is just a short video showing the ion drive in operation, showing it tilting left and right. That's the neutralizer, and then the main ion drive will start up shortly. There it goes. And you'll see it tip back and forth to the left and right with the gimbals. These things are about 10 times more efficient than chemical rockets. Oops. Go in here. Okay. So this is just a diagram showing the kinds of things you have to do for the spiral thrusting algorithm, and some of the mathematics involved. So it's fairly complicated. The student did a really nice job on that. The next thing we're adding is what's called the JT65 weak signal protocol. So currently, like the Marco satellites, which accompanied the InSight lander a few months ago and sent data back during the landing sequence on Mars, were 6U CubeSats like the one I described and had a picture of. They were using the Deep Space Network, which I'll show you one of their antennas a little later. They're 70-meter antennas, so like 230 feet across. But they get a lot of use because anyone who goes to deep space has to use these. There are 3 of them, depending on which way you're pointed. One in Goldstown, California, Madrid, and Canberra. And so there was a protocol that's been developed that ham radio people have been using for a few years by Joe Taylor, one of my physics professors at UMass. He then won the Nobel Prize in 1993. And this tells a little bit about the data on the signal protocol. This would allow a CubeSat to talk to a university ground station using one of the old satellite TV dishes that you see in everybody's lawns driving around in Vermont from Jupiter. And we were testing it bouncing signals off the moon, and it worked quite well. And bouncing a signal off the moon is the same difficulty as going from Jupiter back to a university. This is one of the Marco satellites. It was the data relay, and that's a really neat flat fold-up antenna on the right. That's a reflect array. And I read the article describing how it worked, and I couldn't quite fully understand it, but we were lucky, my colleague and I, we met with the designer for an hour and a half at JPL last summer, and so now I understand how it works. It's just a really clever thing, folds up, doesn't take any room, and is the same as a big dish in its capabilities. So we have this software called CubeOS, which is developed from what we had in our CubeSat, written in Spark, based for people to use in other projects. And currently we have the University of Bridgeport and a high school in California using it. And we just got contacted by MIT last week, and they may wind up using it on a multi-university project. There are like 4 schools that are building a CubeSat. And this just shows some stuff about that software, a little bit about the architecture. And so it's available. We have it on what's called GitHub, where people can go and download the software. It shows some of the modules that are in there and what they can do. Iris is a X-band radio that Marco satellite used Iris, and various things. The bit 3 is the ion drive and so on. Okay, any questions?
Okay, I have a question.
Yes.
So what are the main applications? I really understand bits and pieces of what you said.
Oh, for CubeSats particularly, or yeah?
Where are you headed? What are you really trying to do with it in the future? And really, what are the exciting elements about it that you're still looking at developing?
Well, the timing is great for this. On the front page of the New York Times today is an article about CubeSats. And CubeSats are a small fraction of the cost of large spacecraft. So, I mean, a typical low Earth orbit spacecraft is going to be in the hundreds of millions of dollars, and some of the deep space things are in the billions of dollars. And you can do a lot of things with CubeSats with the miniaturization that has occurred. CubeSats, the proposal was about 15 years ago, and it was an idea from Jordi Puig-Suari at Cal Poly and Bob Twiggs at Stanford to come up with a standardized device. The structure is the same, so it could fit in the same launch vehicle boxes and all of that kind of stuff. So students at universities could build satellites that would be reasonable in cost to get launched because they were small. And when they were first started, NASA and Boeing and all the other space companies thought they were jokes because they were these little tiny things, couldn't be useful at all. Well, as what happens over time, the miniaturization of electronics happens very quickly. Things get better and better and better, that all of a sudden universities were doing real science with these things, and then everybody else got on board. So the National Reconnaissance Office uses them, Boeing makes them, NASA makes them, and those were the first deep space ones, the ones that accompanied the Marco that went along with the InSight lander. And those were like, I think it was around $16 million for the two of them. And to have any other kind of accompanying spacecraft would have been over $100 million each. So that was very useful. And what the problem for the universities was that everybody else got involved in them, and they started bidding up the prices of the launch slots for these things. So it started out, it was $20,000 or $30,000, which is reasonable to raise. And pretty soon it was up to $125,000. And then Garrett Skrobot, who manifests big satellites at Kennedy, decided this would be a great thing for NASA to do. So that we pay for launches. Why don't we put some of these CubeSats on that we fund the development of on our launches, and we can keep the price down. And so initially we're going to charge the $30,000, as I mentioned, and then it turned out they didn't charge anything if you got accepted. It's a competitive thing to be accepted. We were in the first group that got accepted. Because the idea was to test some of the technologies we'd use to go to the moon, and no one had ever talked about that before. So that was pretty good. But they can do all kinds of things. There is a company called Planet Labs. If you go look at their website, they make little 3U CubeSats, like the two of those stacked up together, that have a Maksutov lens telescope in them, and they take pictures of the Earth, and they have a couple of hundred of them in orbit, and they photograph every square inch of the Earth at least once a day. And there's amazing things you can do with current space. They're not the resolution, they can see something the size of a car, maybe a person occasionally. But there's a lot of stuff that's very useful for that, looking at agricultural things and looking at what's going on in wars and so on and on and on. And it's really neat technology. And those are 4 by 4 by 12 inches.
So is the government looking at these pretty heavily?
Well, yeah, they're doing experiments. NASA has some, and the National Reconnaissance Office, the spy satellite people, has done stuff with them. They don't say what they're doing with them. And there are probably some other ones that are being used by the military. As I mentioned, the Air Force launch that we were on had 14 Air Force satellites, but they don't tell you what they are. They were all classified. It's sort of funny, we went in there where we had to put our satellite in the thing that holds them all. It was at the Air Force Research Lab at Albuquerque. And we're in this, and there's a big blue curtain there. It says, don't look behind the curtain. It's sort of like the Wizard of Oz, because it was classified stuff that was going on back there.
So does Vermont Tech plan on marketing any of this?
Well, we're not a commercial business. Our idea is to help other universities who want to put up satellites have them work. So how to use our software. And so that's starting to happen. We have University of Bridgeport now, and this high school in California that has some NASA people working with them are currently working on it. That's all within the last year, using our software. And then I heard from MIT last week, so that's a possibility too. It's sort of nice because MIT launched a satellite, didn't work. And UNH, they launched when it didn't work. West Point launched when it didn't work. University of Florida launched when it didn't work. And then the other 8 that were launched with us didn't work at all. Initially, they were never heard from. And 2 others which had partial contact, one from the Naval Research Lab, the Naval Postgraduate School, and one was, I remember what the other one was. Oh, no, I don't remember what the other one was. That had partial contact for a day. Oh yeah, University of Louisiana in Lafayette. And they may be using our stuff because they were doing a second one, And I asked them at a conference, well, what language are you using? And they looked very embarrassed, said, well, we're going to use C. And I said, didn't you learn anything from your previous launch? So I ran into this guy last September at a NASA Academy of Aerospace Quality and at NASA Glenn in Cleveland, and he said they're looking at it, going to using our software. So that's another one.
Is this patentable? Is it something you can actually?
Well, it probably would be, but you know, we're not doing it to make money. We're doing it to, you know, it's sort of like I have a Tesla, and it's sort of like what Elon Musk does. All his patents are online, available for anyone to use for free. And his idea is to have people everybody have electric cars.
What if you made money and then gave college?
All right.
people
I'm
so
going
they
to
can
stop
go
it
to-
right there. Sorry, hi everybody. Sorry, in the essence of time. If you would like to talk personally to
Okay.
Dr. Brandon right after.
He asked if there was any questions.
I know. But just in this, thank you so much, Dr. Brandon, for being here today. And
You're welcome.
please, we have one more Montshire Talk program next Tuesday, the Sound of Series. It's a musical performance, really out of this world, literally like being in a planetarium and watching this awesome band perform. But once again, let's give everybody.